Hey guys, BuildZoid here, and welcome to the potential part 1 of explaining what most of the DDR4 timings do in terms of like performance impacts. And the reason I say potential part 1 is because this is incredibly tedious and like boring and just a general pain to like do. So if nobody watches this, or if not enough people watch this, I'm just not gonna do a part 2, because while there are other unpopular videos on my channel, I have fun making those. I am not having fun making this. Not really. Like, yeah. I am a big fan of spreadsheets, but this is not my kind of spreadsheet. So, yeah. Anyway, what we're looking at here, well, the way this is supposed to work, if this becomes a series of videos, is we're going to be taking a look at the timings in terms of what they do for, like, performance in various memory access patterns. Which you might be like, why can't we just look at each individual timing on its own? And the reason we can't do that is because RAM is really simple. And also, actually, I should have told you to watch the previous video I made about how memory timings work and why we even have them. You should watch that first, and then this will make a lot more sense. But anyway, back to what I was talking about here. The reason we need to look at actual like scenarios is because RAM is extremely simple. There are, like, once the RAM is up and running, there are only 8 commands that you actually really have to use, right? Like, the rest of the commands for memory are basically to get it set up and running. Once it's running, you only really need to, like, refresh it, read, write, and pre-charge it. And there's, a few different variations of, like, say, the pre-charge command and the read command. Like, you have read with auto pre-charge, write with auto pre-charge. There's a pre-charge all, as well as just a regular pre-charge. Like, so we have a few different, like, so really you could sort of simplify it down to only having like 5 commands-ish, right? If you ignore the sort of like, does the same thing as another command just more automatically, which would be like read auto pre-charge. So yeah, there's really not that many commands that you send to memory, but there are so many memory timings. And the reason we have so many memory timings is because the memory timings describe extremely specific sequences of commands in relation to locations in the memory. So if you're just doing a nice, if you're doing the simplest possible read operation, that involves 3 timings, which is what we're going to be taking a look at today. So we're literally just activating a row, because if you don't have a row active, you can't read anything. And then we're going to send a read command, and we're going to read some data from that row. This is the simplest possible read operation that you could do with a DDR4 memory chip. However, if you want to read 2 locations in the memory if we wanted to do another read, okay, from this point, we need at least 1 more timing. And depending on where exactly that read ends up being, the timing is different. Like what timing we need is different depending on where that read is supposed to go. And worst case scenario, there's actually, if you want to do 2 reads, you can actually end up using 2 more timings instead of just 1 more timing, depending on what, specifically what part of the memory are you trying to read with that second read command relative to the first one. And that's why we have so many memory timings, because there are very few commands, but how quickly you can, when you want to, when can you send those commands without corrupting your data is extremely specific to where is the data, where is the data, and what was the previous command, right? So that's kind of the thing. So today we're just taking a look at the simplest possible thing of just a single read command. And now let's talk about how this spreadsheet works. So what we've got over here is basically a simplified timing diagram. So over here, CK is just tracking which clock cycle we're on. For the purposes of this video, all of the memory timings are assumed to be at 3600 megabits per second, so the memory is running at 1.8 gigahertz. And consequently, at 1.8 gigahertz, our clock cycle takes 0.555 repeating nanoseconds. So over here, this column is tracking how many nanoseconds have elapsed. And we start on 0, which I think actually might be incorrect because like this would probably be 0.5. So yeah, this might be off by like half a nanosecond in terms of the final timing, but it doesn't matter. Like basically, this is just to track how many nanoseconds have elapsed. Actually, no, it isn't incorrect. No, it's fine. Okay, this is why I said this is just absolute pain to set up. Um, anyway, yeah, so we're tracking like nanoseconds over here, which like you need a memory speed to be able to track the nanoseconds because the timings are always relative to the clock of the memory. So at different clock speeds, the nanoseconds column would be different. But for the purpose, like this video, everything is at 3600 megabits per second. Therefore, everything is at 1.8 gigahertz. Anyway, this column over here is our command bus. This is where we send our commands. So we send like activate commands and read commands. And if we were doing something more complicated than this, we would potentially be sending write commands and read with auto precharge or precharge commands or precharge all commands. Like all of the different commands go on the command column. Then we have these two columns over here, well, these three columns over here, which basically specify where in the memory we want to be applying these commands. So this first part is a DDR4 and DDR5 thing. DDR4 and DDR5 have something known as bank groups. It's just an internal, like, organizational thing of the memory chip. You can kind of think of it like a postcode for a city, right? Like, yeah, if you think of the entire memory chip as a city, this is like a postcode in the city, and this is like a specific street, and this is a skyscraper because there are many, many, many rows. um, Actually, no, that analogy kind of breaks down. Anyway, we're just not going to worry about that. Like, this is just part of the just an address to point to a location in the memory. Same goes for the bank. Each bank group has 4 banks. Then we have the row and column address. The row and column is multi-purpose. And the reason it's multi-purpose is because it reduces the pin count on the memory chips, which means higher potential density. As in, you can squeeze more memory chips into less space if the memory chips just have less pins on them. Anyway, so that's why it's multi-column, and basically here, I mean multi-purpose. So if you're sending, and it's multi-purpose depending on what command you're sending. So it's always, like for activate commands, you're always specifying a row. For read commands, you're always specifying a column, right? That's just kind of how that works. Yeah, so that's sort of the address portion of this. And then we have the data queue. This is where the actual data travels between our CPU's memory controller and the memory chips. So yeah, and because DDR is double data rate, in this scenario where we're doing a read operation, we're actually reading 2 columns per clock cycle, right? And also a read, like another thing worth noting is that I'm not sure about DDR3, but like DDR4, DDR5 operate on on bursts. So when you send a read command, you're specifying where to start reading from, and then it'll automatically read for the next 8 columns. So it'll read like for in this scenario, we're reading on column 12. So we start at 12 and we read column 12, like the memory chip outputs the data from column 12, column 13, column 14, 15, 16, 17, 18, and 19. And that's 8 columns. And it outputs all of this data in just 4 clock cycles because double data rate is magical like that. Also, because of double data rate, it would be impossible to have memory like if the reason why we have bursts is because if you didn't do bursts, the fastest you could go could be like single data rate, unless you somehow had double data rate commands, which we don't. So yeah. So this is sort of just like an like a design optimization for, I guess, cost in a way. And it's just kind of unlikely that you would be reading only a single column of data. So yeah, and if you're reading a lot of data, this is just more efficient, right? Being able to just fire off like, I want to read column 12, and then I want to read column, like after you read all of from 12 to 19, you just say, hey, I want to read from 20 to 27, I think. Anyway, so that kind of thing. And then from like 28 to, you get the idea. So anyway, that's how this works. Is like here we have our data, here we have our address, like address of where the data is supposed to come from, or where we want to put the data if we were looking at write operations, but today we're just doing reads. What we want to do, right? What we want to do, that's our commands. And then here we're keeping track of time, and here we're keeping track of clock cycles. So anyway, let's get into this. So this is a single read operation with timings of like the idea, like the basis of this configuration right here is, like a custom overclock of some Samsung B-die of doing like 3600, 14, 13, 11, 21, 1T. This is achievable on good sticks of Samsung B-die with, actually really good sticks will do this on less than 1.5 volts. Not so great sticks might need 1.55 volts for that tRCD 13 over there. Anyway, so this is like a realistic overclock that you could achieve. As for what platform you would want to... This is like, if you're on Threadripper, you might be looking at something like this. Because on mainstream Ryzen, there's really no reason to be at 3600. Like 3666 and 3733 are totally viable. Threadripper's Infinity Fabric, on the other hand, is even worse than and when I say Threadripper, I mean Threadripper 3000, not the 5000 stuff. I don't know how that behaves, but yeah, anyway. So this is like Threadripper. I guess maybe if you're on X299, you might run something like this as well. So there's not really a lot of platforms where this is like peak performance, but it is a viable manual like Samsung B-die overclock. Anyway, so since we're just doing a read, the only relevant timings are our cast latency, our tRCD, and our command rate. For convenience in this example, I've set the command rate to 1. Funnily enough, for like Intel platforms, command rate default, like the default behavior for the command rate is to be actually 2 cycle command rate, not 1 cycle command rate. But anyway, we'll get to that. That's why we have multiple scenarios to look at today. And then tRCD 13 and tCL 14. So the way this works is we need to start by activating a row in the memory because we're starting with the memory completely idle for this read operation. And so we send an activate command, and we say we want to activate row 123. Incidentally, there are like thousands of rows in a bank. Like when I say thousands, I mean thousands. Like 65,000 rows in a bank is a totally normal amount of like rows to have in a DDR4 in a bank of a DDR4 memory chip. How many rows you have actually depends on how dense the memory chip is. And each row is 1024 columns long, and each column is 8 bits deep. Well, actually, no, the depth of the column depends on the width of the memory chip, but they can be typical memory chips, like X8 memory chips, will be 8 bits deep. I am going to have to put so many links in the description to cover all the like stuff you need to know about RAM before watching this. Yay me. I hate this. I hate this so much. Anyway, so what we're saying here on clock cycle 0 is that we want to activate row 123 of bank A of bank group A. And then we wait for 13 clock cycles because our tRCD is 13. So we don't do anything for 13 clock cycles. And the reason we don't do anything for 13 clock cycles is because the memory chip takes some time to activate the row. We don't know how long it takes, but if we don't wait long enough, our data gets corrupted. So and this is a B-die memory chip, and those typically, at these kinds of settings are realistic for B-die. So completing a row activation in like 7.22 nanoseconds is actually, in the grand scheme of DDR4, very fast. It's a very fast row activate. Like in less than 7.22 nanoseconds is a very fast row activation right there. But that's why I'm saying Samsung B-die. Also, we're kind of mashing voltage into it. Anyway, so on cycle 13, because our tRCD is 13, we send our read command. And with our read command, we say we want to read column 12 of whatever row we activated in bank A of bank group A, right? And so we say that. And then because our cast latency is 14, it takes 14 cycles for the memory chip to basically output the data. Well, it basically output the data to the data bus. Right? And then once it starts out, like this is the first 2 columns in clock cycle 27 over here, because it's literally it's 14 cycles after our read, so that ends up on cycle 27. So we get columns 12 and 13, then columns 14 and 15 on cycle 28, 16 and 17 on 29, and 18 and 19 on 30. And so in 16.67 nanoseconds, we have managed to read, like if we're talking about a standard DDR4 memory stick, 64 bytes of data. Because each column is the memory stick is 64 bits wide, and so each of these columns actually represents a 64-bit data transfer, right? So here we're transferring 64 bits times 2 plus another 64 bits times 2, and then you divide your bits by wait, is that working out? 64 bytes? No, 8 bytes. Did I screw up? I might have screwed up the math. I have 8 columns, or times 64, divide by 8. Oh no, I didn't screw up the math. It is 64 bytes. Yeah, it always gets me just like how large, like a read burst is sort of the default size for a read operation with DDR. It always gets me how much data that actually is. Anyway, yeah, so it is just straight up 64 bytes of data right there. Anyway, so this is what it looks like if you have like very tight timings, and yeah, we get our data within, or more like the data is output from the memory chip in 15 nanoseconds. It still takes time for the data to actually like, get down the motherboard, which doesn't really take that long, but then it takes quite a while to get through, say, your memory controller, and then the ring or the infinity fabric, and then it needs to get to the cores. So that's kind of the thing, is like this is this latent, like this nanosecond number we have on the side here, this is like pure memory latency. It doesn't account for the internal latency of the CPU once the data gets to the CPU. So yeah, this is how long every thing takes at the end of the memory stick, like on the memory stick end of the operation. How long it actually takes for the cores to see your data depends on a lot of other factors. Anyway, so this is like an aggressive timing, like a single read, like the most basic read operation possible with some pretty aggressive timings. Now, for comparison here, we have a like pretty normal XMP. Actually, not a pretty normal XMP, like a good BDI XMP, right? 3600, 14, 15, 15, 35, 2T, 1.45 volts. Literally stole those timings from this G.Skill memory kit. So tCL is 14, tRCD is 15, and the default behavior for command rate, we're assuming an Intel memory system for convenience here. The default behavior for command rate is to actually default to 2T, especially once you're at something like 3600 megabits per second. And the reason you would have a 2-tick command rate, or like 2-cycle command rate, is because if there's any kind of like signal integrity issue or timing mismatch between the memory stick and the memory controller, if you just hold the command on the command bus longer, it's a lot easier to read it, right? It basically just makes it easier. Like it's like if you're yelling instructions at somebody, it's the difference between yelling the instructions very quickly and then like yelling them slower, except think of it more like a continuous beep versus a short beep, to indicate that something is finished, right? Rather than like yelling words, because that's not how it works. Like all of this arrives at the memory chip at the same time. Like this is a parallel thing, right? Like these are, yeah. But anyway, so we basically hold our activate command for 2 cycles, and we hold our address information for 2 cycles, so that the memory chip has an easier time picking up on it. Which also means that now it takes, like now instead of starting, like the count for our tRCD on cycle 0, we're starting the count for tRCD on cycle 1, because we've just spent 2 cycles holding the command so that the memory chip can read it. And again, we're just going to be reading row 123 of bank A of bank group A. And we're going to wait 15 cycles this time, right? So we're waiting from cycle 1 to 16. And then we send our read command. And again, we hold that read command for 2 cycles because we have 2-tick command rate. And so, yeah, and again, we're specifying that we want to read from column 12 of bank A, bank group A. And 14 cycles later, because our cast latency is 14, we get our data, right? But because our like tRCD is 2 ticks longer, and also because we're spending 1 more cycle on every command, our data actually starts getting output from the memory chip on clock cycle 31 instead of clock cycle 27. So we've just added like 2.2 nanoseconds of latency to our memory by just increasing tRCD by 2 and command rate by 1. Command rate by 1. Because every single command is now taking an extra clock cycle to basically register at the memory chip. Anyway, so this is like an aggressive XMP, right? Like this, there are even better XMPs, but I didn't want an XMP where the tRCD is 14 because then we like it's just no, like I want variety in the timings. Like like it would literally, like if the tRCD was 14, all that would happen is this block right here, well, everything would get moved up by 1. Right, like instead of the read the data actually being output from the memory chip at like starting to output from the memory chip at 31, it would be at 30 because the read would be on 15 instead of 16. Anyway, now let's take a look at what I consider like a normie XMP, which I've realized retroactively is like not actually very normie, because like what's this then? I mean, to me, this is trashed here. RAM is RAM kind of XMP. This is what you buy when your interest in RAM is on the level of like it's just RAM. I do not care. This is like I really don't want Samsung CDI in my life because Samsung CDI is bad for your life. This is a Hynix CJR bin, by the way. Generally, it could also be DJR at this point, but I think CJR is still plentiful. Anyway, so now we're looking at like 16, 19, 19, 39, 2T, 1.35 volts. So our command rate is still 2, and actually, well, yeah, it's still 2. tRCD is 19, tCL is 16. So we send our activate command, we hold it for 2 clock cycles, row 1, 2, 3, bank A, bank group A, same thing, right? And now our read command, because our tRCD is 19, we can only, we have to wait 19 clock cycles from cycle 1 to send our read command, so that ends up being on cycle 20. Again, we want to read column 12 of bank A of bank group A, and again, command rate 2, so we're holding it for 2 cycles. And because our cast latency is 16, 16 cycles after the end of our read command, we actually get our data, which is now on cycle 37. So 20 nanoseconds before the memory chip starts at 20.5 nanoseconds before the memory chip starts outputting data, which is like a whole 5 nanosecond, basically like 5 nanoseconds longer than our very tight timings. And now we get the loose XMP, right? Which just 18, 22 tRCD. It takes a while for anything to happen with this. So we send our activate command, and then the RAM takes its sweet time activating row 123 of bank A, bank group A. So we can only send our read command 11.6, because the thing is we're from 0.56 over here, so it's not actually 12.2 nanoseconds. Actually, no, it is like 12.2 nanoseconds because the command's on 23. Just, we wait like 12 nanoseconds before we send our read command, and then again, we're holding that read command for 2 clock cycles, and then, 18 cycles after our read command, we finally get our data on clock cycle 42. 23.3 nanoseconds from the start of this timing diagram. Wait, is that right? 42? 24 plus 18, 42. Yeah, okay, that is correct. Yeah, okay, there's no mistakes in this. So, yeah, and this is a single read operation with terrible timings, Hynix CJR timings, right? It's got slightly lower latency. Actually, Micron Rev E will also do very similar timings. Then we have a tight XMP profile from Samsung BDI, which a bit faster, and then we have a very tight where we're doing 15 nanoseconds instead of And it's not really it's not that big a difference. Well, each step is individually not that big a difference, but going from the 14, 13, 11, from the 14, 13 profile to the 18, 22 is quite a gap, right? We're going from like 15 nanoseconds to 23.3 nanoseconds, which is like an 8.3, yeah, that's 8.33 nanoseconds less latency or more latency depending on which direction you're looking at it in, right? Like this is 8.3 nanoseconds more. This is 8.3 nanoseconds less than the 1822. Anyway, so yeah, that's that's the simplest possible read operation. If we wanted to do another read after this, things get way more complicated depending on where that read is going to be. And we're not going to get into that this video because this video is 25 minutes long. So yeah, I'd love to hear your feedback on this because these timing diagrams are kind of a pain to like do. I should have done this with DDR3 just because there'd be less idle time. Right? Because like DDR3 timings are single digits instead of this horrible mess. But yeah, hopefully this makes sense. That's one of my main concerns because like I know right now this is an extremely simple timing diagram, but some of the other ones I have in store are things like well, this one's fun. This one's really filled out. Actually, for DDR3, this one would be horrible to do. So yeah, this one's very full. Then we also have like the worse version of that, which is very long. We have, oh yeah, IDA style. We have, wait, what is this? No, this is just like, oh, this is an old version of the read command, but then we have like this. So yeah, and I'm not done with making all the different, like, well, I'm not going to necessarily cover every single possible scenario, but I want to cover scenarios that are like interesting or like important to perform, like important to understand, maybe something like that. I'm not really sure. But yeah, so I'd love to hear your feedback on like, does this make sense? Am I being too slow with this, perhaps? Because I know I just dedicated like a 30-minute video to just a single read operation, but like, yeah, I'm really not sure. Like I don't really want to be doing this again with like all these different freaking different XMPs, like in the like XMP profiles. Like in the future, I would probably just do like 2 different timing configurations to show the difference instead of like 3. Because really, like after the first 2, I feel like you should get what's going on here, right? Is like this is tight, this is loose, this is looser. This is like you just as your timings get bigger, you just keep adding more and more delay between your commands. At least for this scenario, there are some scenarios where because of yeah, well, okay. I'll figure that out when I get to it, but yeah. So that's it for the video. Thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. It would be much appreciated if you'd check that out. Also, there's a decent chance that the patrons might get access to this spreadsheet, and there are some like extra text posts for available for patrons. It's all information that I've technically covered in videos, but condensed. So you don't have to sit through like 30 minutes of video. Anyway, where was I going with this? Right, Patreon would be much appreciated if you check that out. I also have a Teespring store. There's a link to that down in the description below. And then there's also then I also have a Bandcamp, which you might want to check out. There's a link to that in the description as well. So that's it for the video. Thank you for watching, and goodbye.